You have been taught that entity repository patterns are a universal best practice for organizing code. You were told they make your application readable, maintainable, and clean. But in the era of modern AI pipelines, this dogma might be silently starving your GPU clusters. When you structure data retrieval around rigid object hierarchies, you introduce serialization overheads that force high-performance hardware to idle while waiting for transformation. The stakes are not just about code quality, they are directly tied to compute costs and carbon emissions. Today, we connect the dots between a common architectural pattern and the hidden latency bottlenecks crippling your training cycles. Let us start by challenging the assumption that clean, object-oriented design is always superior. In traditional software development, separating data from logic was a victory for maintainability. However, generative information retrieval systems operate under different constraints. When you feed massive vector stores to GPU or TPU clusters, every millisecond spent serializing and deserializing objects becomes a second of hardware wasted. Recent research into these pipelines identifies that rigid entity repository structures create critical latency bottlenecks. While this pattern excels at local code organization on your laptop, it introduces significant I/O delays during retrieval-augmented generation. The system spends disproportionate time moving data between disk and memory rather than computing vectors. This is the efficiency paradox where optimizing for readability locally starves throughput globally. The mechanics of this latency are subtle but devastating in high-throughput environments. In a standard RAG workflow, your application must extract entities from unstructured text, serialize them into objects, pass them through repositories, and then deserialize them again before they reach the vector database. Each step adds CPU cycles to the pipeline that could otherwise be spent on inference or training. The result is a hidden cost, where your expensive hardware sits idle, waiting for data transformation tasks to complete. This delay does not just slow down user queries, it extends the time required to process large datasets during model retraining phases. When you are running high-scale vector stores that must feed clusters in real time, this architectural friction becomes a primary driver of reduced inference throughput and elongated training cycles. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. We need to look at the hardware reality check immediately because software lag has physical consequences. Inefficient architecture amplifies AI's environmental footprint significantly. Studies indicate that operational serving of large language models is beginning to exceed training in total energy consumption, meaning your day-to-day infrastructure now burns more power than your initial model development did. When you rely on serialization-heavy pipelines, the cluster cannot maintain a steady stream of workloads. This leads to inflated energy bills and increased e-waste as teams upgrade machines to compensate for software slowness rather than optimizing code paths. One recent study highlighted that over 40% of subjects treated AI tools as an infallible predictive authority without questioning these underlying inefficiencies, leading individuals to self-constrain their decision-making processes regarding resource usage. This brings us to the behavioral trap where developers often trust automated tools to fix complex pipelines without understanding the EIO costs involved. When you rely on code generation assistants to build out standard entity repository layers for every new feature, you are effectively outsourcing architectural judgment. A startling finding from a large-scale study involving over 1,300 participants showed that more than 40% treated AI as an infallible predictive authority, leading them to accept generated solutions without critical review. The result is unpredictable credit consumption and financial risk when scaling up operations. We have seen reports of users depleting their entire monthly allowance in just 2 days because the underlying pipeline inefficiencies caused runaway costs that no one anticipated until the bill arrived. The pressure to fix these bottlenecks often leads to a cycle where teams upgrade hardware faster than they optimize software, creating unnecessary carbon emissions and e-waste. Model size and frequent versioning are primary drivers of higher emissions, yet we continue to layer complex object hierarchies on top of simple data access needs. The organizational context dictates impact. University-led projects currently generate the highest emissions due to iterative retraining driven by these pipeline bottlenecks. We must shift our engineering judgment from writing readable code to designing data flow-efficient pipelines that respect the constraints of high-performance compute resources. So, what is the prescription for breaking this dogma? You need a decision framework that identifies when an entity repository pattern is appropriate versus when it becomes a liability. For low-throughput applications with complex business logic, traditional patterns remain valid. However, in high-scale AI inference and training scenarios where zero-copy or direct vector streaming is required, you must abandon the rigid separation of data and processing layers. Start measuring clean code against cluster efficiency by monitoring how long your GPUs spend idle waiting for serialization tasks to complete. If a significant portion of your compute budget is consumed by moving data rather than computing vectors, it is time to refactor your architecture toward direct access patterns that minimize transformation overheads. The shift from optimizing for local readability to global throughput represents a fundamental change in engineering judgment for the AI era. Architects who prioritize clean, object hierarchies at the expense of vector throughput are effectively burning compute budget and increasing their organization's carbon footprint. By understanding these trade-offs, you can advocate for architectural changes that reduce serialization and directly impact operational costs. This is not about abandoning best practices. It is about recognizing that in the context of AI infrastructure, data flow efficiency supersedes code structure elegance when hardware utilization is at stake. The most valuable skill you can develop now is the ability to look at a familiar pattern and ask if it is actually costing your cluster its time. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.